So here's our second video in redox reactions, and in this video we're going to learn how to balance redox reactions using oxidation numbers. So it's one method that we can use to balance these reactions. The reason why we teach this to you is because there are some reactions that you cannot balance just by looking at them. They get a lot trickier. So if you follow these steps, you should be able to balance them no problem. It's just going to be a little bit different than what you learned in grade 11. So easiest way to talk you through a balancing reaction question is to just go straight into an example. So here's example number 1. Write a balanced net ionic equation to show the combustion of ammonia and oxygen that produces nitrogen dioxide and water. So obviously our first step here, write out a balanced equation. Or sorry, not a balanced, an unbalanced equation. So I have ammonia and oxygen on my reactant side, and I have nitrogen dioxide and water on my product side. Step 2. In this case, will be to assign oxidation numbers to each element. So this, I hope, should be easy for you all right now. So if I just rewrite my equation there, and I assign my oxidation numbers using those 7 rules from the last video, I get these answers here. Now, I'm not going to show you how I got all of those, because that is in the first video, but at least you can kind of see where that's going. Oh, fancy schmancy. Here we go. So now I'm going to identify the changes in oxidation numbers as oxidation or reduction. So again, here's my reaction, here are my oxidation numbers, nothing really new there. But I can see that my nitrogen is changing from -3 up to +4, and my oxygen is changing from 0 to -2. Okay, so you can easily see that. So we're going to sort of look at that in more detail. So what happens? My nitrogen is being oxidized, so NH3 becomes NO2, and I end up with 7 electrons that are lost. My oxygen's getting reduced, and it's going to gain 4 electrons to form the 2- charge in NO2. Notice I'm ignoring water for now. I'm doing that on purpose. Always ignore water unless there's no other option. That's kind of a rule of thumb just to make your life a lot easier in these examples. So my next step is to find the numerical value for the changes in oxidation number. So if I fill in this chart down here, I'm looking at, to start, my initial oxidation number on nitrogen, which was -3. Final oxidation number was +4. So that means it changed by, it changed by 7. So it lost 7. My oxygen, on the other hand, started off at 0 and ended up at -2, so it had to gain 2 electrons. Ooh, sorry. It had to gain 4 electrons. So now you might ask, why 4? It's because I had 2 oxygens over here. So each oxygen gained 2 electrons, so I have a total change of 4 electrons. So what I'm going to do is multiply each one to get the lowest common multiple. So I'll times the top one by 4 and the bottom one by 7, so that I end up with -28 electrons on the top and +28 electrons on the bottom. So that's important. You don't necessarily have to fill in a chart like that, but sometimes, I don't know, I put it in there because sometimes it helps people keep everything organized. So there we go. So now that we know our electron loss and gain, we're going to balance it by multiplying, just like I did, finding the lowest common multiple. So nitrogen increases by 7, oxygen decreases by 4, so the lowest common multiple is 28. So here's my ratio. So here's what I do. I'm going to take my nitrogen reaction and I'm going to multiply it by 4. I'm going to take my oxygen reaction and multiply it by 7. So here's what you have to remember to do, is when you actually do this, your electrons should cancel out. So if I look, I should have 28 electrons on either side of my reaction. And I'm only going to put the coefficients on the reactant side of my equation, okay? So because I times this reaction here by 4, I put the 4 in front of NH3 there. Because I timed this reaction by 7, I put the 7 in front of my O2. And again, I did that so that I would have 28 electrons on the reactant side and 28 electrons on the product side, so that they end up canceling each other out. So now what do I do? Now I can balance the other elements by inspection. So I have the 4 and the 7 that I've already added in. If I look at my balancing, I need 4 NO2 and 6 H2O. Okay, so instead of trying to figure this out right from the get-go, you can use your oxidation numbers to find your coefficients of your reactants and then use that to find the rest. So that's your final answer, sorry. For example number 2, again, we're going to balance this reaction using the oxidation number method. So here's a perfect example of a reaction that just gets a little bit crazy, and you want to make sure that you're actually like doing it and you're saving yourself some time. So you need to follow these steps that I gave you. So again, you have your unbalanced reaction, and you're going to assign your oxidation numbers. Where are my oxidation numbers? Oh, they're not there. Okay, I guess I have to put them in. Let me just do this here. So I'm going to assign oxidation numbers to everything in here. So let's start over here. So hydrogen has +1, oxygen has -2. So overall your carbon, so 3 carbons plus 8 hydrogens plus 1 oxygen has to equal 0. Okay, so 3 carbons, sorry, plus 8 minus 2 equals 0. So I end up with carbon being 2. -2. I hope I did that right. And let's figure out the rest. I'm going to do some different colors here. So this is -2, this is +6. -2 plus 6 and +1. Again, this is going to be +6 minus 2. And in this case, this is going to be +3. The C3H8 H6O is going to be -2 plus 1, so that's 6, 4/3, and -2 and +1. So there we go. So there are my oxidation numbers. So in this reaction, oh shoot. Oh, I just lost them all. Okay. My oxidation number of chromium is decreasing from 6 down to 3, and my oxidation of carbon increases, I think from 2 to 4/3. So let's make the number of atoms that change oxidation numbers the same on both sides by inserting temporary coefficients. So what I'm going to do is I put a 2 in front of my CrO3 to make sure that I have the same coefficients on both sides. So my chromium changes from +6 to +3. My carbon changes from -2 to -4/3. So if we look, this is where you have to keep in mind that you've got more than one element within a compound. So I've got 2 chromiums here. Oops, oh shit. Why isn't this working very well for me? So I've got 2 chromiums here and only 1 chromium there. So I added in this extra coefficient just to start to balance off the chromium. But then when I take that into consideration for the number of electrons, I have to take into consideration that I'm decreasing my oxidation number from 6 to 3, but I'm doing it 2 times. So my total decrease is 6. It's basically 3 times 2. For the carbon, it looks like it's tricky because you've got a fraction in here, but it's actually not. So don't freak out just because you have a fraction, because again, the fraction sort of ends up canceling each other out a little bit because you can't have a fraction of an electron moving. So if we look, my oxidation number on carbon to start with was -2, and then it went to -4/3. So the total increase is actually 2. How did I get that? I had 3 carbons over here, and I end up with 3 carbons on the end. Okay, so what I do is I basically times everything by 3, just like I times my chromium by 2. So when I do that, I'm actually going from -6 to -4. Oops, -4. Okay, so if I take this whole thing and I times it by 3, just like I took this whole thing and times it by 2, then I get that I'm going from 6 to -4, so that's a total increase of 2 electrons. or sorry, a total increase of 2 in your oxidation number because you're taking away extra electrons. So those are going to be my what I'm going to use to balance the equation. So I'm going to use the smallest ratio to balance, so the lowest common multiple is 6. So my chromium, I'm going to leave it alone because I already have 6 electrons moving. My carbon, I'm going to take it and times it by 3 to make it 6. So I kept the 2 that was here, okay, and then I multiplied my carbons. So this one's going to be times 1 to keep 6, and this one's going to be times 3 to make it 6. And this means that my electrons transferred are exactly the same. So that's how I got the 3 in front of each one of my carbons, as you can see in red. And now we can balance the other elements by inspection. So when I do that, I have to put a 3 in front of my hydrogen sulfate or my sulfuric acid and a 6 in front of my water, and then I'm balanced. Acidic and basic solutions is something that we'll talk about in class because I don't want this video to go on for too much longer. So that's it for today.